Now, to be useful in distinguishing wavelengths that are very close to each other, a grating must spread apart the diffraction lines for the various wavelengths. So the amount of spreading is called the dispersion of the grating, and we give it the symbol capital D. The greater D is, the greater the distance between two emission lines whose wavelengths differ by delta lambda. So that means that delta theta is bigger for a particular delta lambda. So to achieve a higher dispersion, you have to use a grating with smaller slit spacing D and use the higher order fringes, which means the ones further away from the center line. Apart from spreading out the wavelengths, we also want to be able to distinguish them, just like a telescope needs to be able to distinguish closely spaced objects. That means we want the lines to be as narrow as possible. So gratings have a resolving power, which is defined in terms of the wavelengths that you can distinguish in the diffraction pattern. If two closely spaced wavelengths are lambda 1 and lambda 2, then the difference between them is delta lambda, and we define the resolving power R of a grating as R equals lambda over delta lambda. To show an example, the spectrum of sodium has two very closely spaced lines called the sodium D lines that are about at 589 nanometers. A good spectrometer will show them clearly as two lines, but with a spectrometer of lower resolution, you just see one fairly thick-looking line. Now we can find an expression for resolving power by going back to the equation we found for the half-width angle of one particular fringe. So we start with the expression for the half-width angle of a line. Delta theta half-width is lambda over nd cos theta. And we want to substitute that angle into the dispersion equation. And we know that the dispersion equation is that delta theta over delta lambda is m over d cos theta. So substituting in the equation for the half-width angle, we get that the half-width angle over delta lambda is lambda over delta lambda nd cos theta, which is m over d cos theta. Now we cancel out the d cos thetas, and then we get lambda over delta lambda times n is the order m. And so we can now get an expression for the resolving power of a grating, which is the wavelength over delta lambda, so the change in wavelengths it can distinguish, equals n, which is the number of lines, times m, which is the order. So now we can tell that if we want to increase the resolving power of a grating, we need more slits, and given that the light will only have a finite width, that means we want to bring the slits as close together as possible, and also we would want to use the higher order fringes that are further out because they are now more spread out. So we'll do an example. Let's say that a diffraction grating has spacing d equals 2 microns, so 2 by 10 to the minus 6 meters. It is illuminated by a sodium vapor lamp that has the two sodium D lines at 589.00 nanometers and 589.59 nanometers. Now the first part A, at what angle does the first order maximum occur for the 589 nanometer line? And B, using the dispersion of the grating, calculate the angular separation between the two lines in the first order. We'll work through this on the tablet. Now, the things we know, we have the spacing of the slits is 2 by 10 to the minus 6 meters, and we have the wavelength of the first line is 589.00 nanometers. Now, first order means m equals 1. So we have m lambda equals d sine theta. So sine theta equals m lambda over d equals 1 times 589 by 10 to the minus 9 over 2 by 10 to the minus 6 equals 0.2945. So theta equals 17.13 degrees. Now, making the assumption that those angles of the two lines are very close together, we want dispersion D at that 589 nanometers. So D at this angle. And D equals M over D, the spacing, cos theta. And we're just taking that one angle. So M is 1, D 2 by 10 to the minus 6, cos of 17.13 degrees. And that is 5.232 by 10 to the minus 4, but dispersion is measured in radians, and we'll do it per nanometer because that's what our wavelengths are mostly in with these calculations. So then using dispersion is delta theta over delta lambda, and that gives us the spread of angle equals dispersion times the spread in wavelength. Now, delta theta equals 5.232 by 10 to the minus 4 times the difference between the wavelengths, which is 589.59 minus 589. And that gives us the 5.232 by 10 to the minus 4 radians per nanometer times 0.59 nanometers, which is 3.087 by 10 to the minus 4 radians. And then we times that by 180 over pi to get 0.0177 degrees.